My name is Zaria Brown, and this is Lab 3, the black hole orbit. By definition, black holes can't be observed directly, so to find the mass of one, we must analyze the gravitational force the hole has on an object of known mass. In this experiment, we are given the fixed position of a black hole and the position and mass of a star orbiting it. In a VPython code, I found the mass of the hole using the momentum principle and Newton's law of gravitation to find the velocity of the star and the perpendicular and parallel components of the net force on the star due solely to the hole's gravity. This yielded the results that by the momentum principle I could find the star's velocity and relate dp dt to Fnet. And then I could use the gravitational law and the given mass and position of the star to find the hole's mass, which I found to be 3.566 e to the 31 kilograms. I went about calculating this through VPython. So I first had to set the scene and create a visualization for the black hole, the star, and the arrows that would represent Fnet, perpendicular, parallel, and just Fnet. Then I went about putting in the values for the star's mass and the timestamp, which is how many seconds are in a day. And then I imported the position data for the star that was also given to us. So now that we have those given values inputted, we can use them to calculate the velocity of the star at any given point. So at each indexed value for the x and y components of the velocity, we can set that the velocity of each one of those is equal to the change in position in whatever component that it is, whether it's x or y, over the change in time. So you'll see the x velocity is indexed at delta x over delta t. The y velocity will be delta y over delta t. So now we have the velocity of the star, which is constantly changing. So at each index value, we'll now take that and change it each time. So v initial will be the vector of whatever was previously indexed, and the y will be whatever is previously indexed, and then v final will be the current index of each component as well. And then p initial, or the initial momentum, will be the mass times that initial velocity, and p final, or final momentum, will be the star's mass times final velocity. And then delta v and delta p will just be final minus initial of those values. And then dp dt, quite frankly, is delta p over delta t, so we'll just rename that value to dp dt. And then by Newton's second law, Fnet is equal to dp dt. So at this point we have Fnet, and we can go about calculating the mass already if we wanted to. But to demonstrate the changing directions of parallel and perpendicular components of Fnet, we have to go and calculate dp dt parallel and perpendicular. Finding p hat will give us the direction of the parallel force, so we can set that equal to p initial over the magnitude of p initial, and then the change in magnitude over time of that will be as follows in that line. And the following line will just set that dp dt parallel is equal to d magnitude of momentum dt times p hat. So the momentum principle states that we can set dp dt parallel equal to Fnet parallel because they're essentially equal. And then we can use that to find dp dt perpendicular because the two components add up to equal dp dt. Then yet again, we can use that momentum principle to set the perpendicular component of dp dt equal to the perpendicular component of Fnet. So now we have the direction and magnitude values for the arrows, so now we can use that to demonstrate how those are being affected as the star orbits the black hole. In this model, the black hole is a black dot, the star is a yellow dot, Fnet is yellow, Fnet perpendicular is blue, and Fnet parallel is black. The arrows grow larger in accordance with an increase in magnitude of Fnet. So it's apparent that the magnitude of the net force is greatest when the star is closest to the black hole. The first two lines you see here are just a reiteration of what I had to use in the code to calculate Fnet. The third line is Newton's law of gravitation, where the magnitude of F gravity, or Fnet in our case, since the only thing acting on the star is the black hole, is equal to g times mass of the star times mass of the black hole, all divided by the distance between the two squared. So knowing that g is equal to 6.7 e to the negative 11, and that the distance between the two can be found by taking the magnitude of basically the star's position minus the black hole's position, we can just rearrange Newton's law of gravitation to solve for the mass of the black hole. From running this code, I found the mass to be 3.5662 e to 31 kilograms. To wrap things up, F-net and dp/dt are directly equal to each other, so their components are also directly equal. And the only way that they are different is that dp/dt is caused by changes in F-net, so any change in the force applied to that will affect the change in momentum over time. To answer the what-if question, no, it is not possible to find the mass of the new hole that's different from the original. If no other values have changed, then we'll always end up with the same answer for the mass of the black hole.